So we'll start week 4, which is the first week of our neuromuscular section, I guess. So for the next 3 weeks, we're going to be talking about the nervous and muscular systems, and really they go hand in hand. We're going to start with a review, and it's kind of a review, but I just want to make sure that this is fresh. We've gone into detail, and we'll make sure that as we go through class that you understand some of these concepts that we talked about during the first week of class, as well as what you learned in your physiology class. So we're going to start off by talking about sarcomeres. And here are the four, I almost said objections, but they're objectives or outcomes, whatever you want to call them. Okay. And so if you recall, a muscle cell has a cell membrane, which is our sarcolemma. It has an endoplasmic reticulum that we call sarcoplasmic reticulum. And in the sarcoplasmic reticulum, that helps regulate the amount of calcium that's in the sarcoplasm, or the egg white of the cell. We've got what's called the terminal cisternae, and that's actually part of the sarcoplasmic reticulum, and that's where the calcium's actually at. And then we've got the T-tubule, and that's basically a big hole. It's actually called an invagination. That goes deep into the muscle cells so that an action potential can travel from the cell membrane down into the muscle cells so that the fibers that are in the middle of a muscle will actually contract. And then we've got the triad, which is where the T-tubule, the sarcoplasmic reticulum, and the terminal cisternae all come together. Now, when it comes to an actual sarcomere or a muscle cell, there are 6 main proteins that make this up. And so we've got actin, which are the thin contractile filaments. And we've got myosin, which are the thick contractile filaments. And so actin is, it's hard, it's kind of hard to see here, but it's this green stuff. And here, the myosin is this purple stuff. And if you notice, myosin has kind of like these golf club heads. And I like this diagram too, and it's easier to see here. In that these myosin heads are all over the place. It's not just like they're on one plane, but they kind of circulate around the whole fiber. And then as you look at actin, it kind of has this circular pattern as well. So this allows all sorts of pulling and winding, and we're going to actually get into that next week when we talk about titin. Okay, so we're going to talk this week about the sliding filament theory, but we've gained more knowledge, and it actually seems to be more of a winding filament as opposed to a sliding filament. But the sliding filament is a little easier to understand, a little easier to conceptualize, so we talk about that. So then what regulates actin and myosin are troponin and tropomyosin, and then we've got titin and nebulin, which are structural proteins. As you can see here, we've got titin, which are these elastic filaments, and that allows the muscle to go back to its resting length after it's contracted. And nebulin, which I don't see on here, I can't remember if it's on here or not. It kind of helps stabilize actin. All right, and so like I said a minute ago, titin is also contractile, but for right now, if I ask about it on a quiz or whatever, because just kind of introducing this, just think of titin as structural. Okay, so don't get caught up yet on titin being contractile. We'll get to that next week. Okay, so just a little more detail or a reminder, depending on what you remember, what you don't remember. Myosin's attached to the M line. It moves actin. It pulls actin towards the M line, and it's the thick filament. Actin are attached to the Z discs. They're the thin filament, and they're pulled towards the M line. It's important to remember that as we go through muscle contraction, the length of these fibers do not change. All that's changing is the amount of overlap. So we've got tropomyosin, which prevents actin and myosin from binding. We've got troponin, which ultimately will move tropomyosin out of the way. So when calcium binds to troponin, that causes everything to kind of rotate. And so tropomyosin moves out of the way so actin and myosin can get together. Okay. And then we've got the bands and zones. So if you look at it here, we're just going to focus on actin and myosin. So actin are the red lines here. Myosin are the blue lines here. So notice that we've got the I band, my highlighter's not working, the A band, and then the H zone. Okay, so the A band is wherever there is myosin, that's the A band, so it includes all of the myosin. There is some overlap with actin, but it doesn't contain all of the actin, or very rarely does it. The H zone, which is here, so basically this part here, or from this range here, that is where there's just, actually, I messed up there. Let me erase that. So we're just going to erase everything here. So the I band, or excuse me, the H zone, I'll get it right. The H zone is where we have myosin, but no actin. So we go from here to here. So where there's just blue, all right? And then the I band is where we have no myosin, but just actin. So this right here is the I band, like it says, okay? Now, if you notice, what happens during contraction? As I said, the A band doesn't change because we don't change the length of any of these myofibrils. These proteins just stay the same length. All that's changing is the amount of overlap. So we've still got, however long this is, the A band stays constant. All that's happened is, with muscle contraction, we've pulled actin towards the middle. So as a result, the H band or H zone gets shorter, as does the I band. And so that is your review of a sarcomere.